All right, as we do our geometry review, as I was just saying, let's remember that we're a team, we're in this together. You catch my mistakes, write a note in the chat so that I know to fix that. If you need me to slow down or repeat something or scroll back up, let me know. It is most helpful if you say, can you scroll back up to number 2 instead of can you just scroll back up a little. I don't know how far to go unless you give me a number in there. It's okay for you guys to make mistakes. We're in it together. Starting our review then. Last year we did a whole bunch with angles, if you recall all those polar coordinates and things that we did. We started talking about angles as rotation. Previously, we just said if you have one ray and then you have another ray and they have the same endpoint, that is an angle. Last year, we started talking about this rotation. If we had the initial side, and then if we imagined moving that side in a counterclockwise direction, keeping the origin fixed, wherever we ended up, we called the terminal side on that angle. We also could end up at that same 30-degree spot if we went around 360 degrees and 30 more. We would still end up with this same terminal side when we went to 390 degrees. We could keep going more and more and more as many times as we could possibly imagine, each time coming up with what we call coterminal angles. And those are just angles, start in the same place, end in the same place. It's just we may go around 30 degrees, or we may go around one full circle and then 30 degrees more, or 2 full circles, 3 full circles, and so on. So we could have 720 plus 30, giving us 750 degrees, and so on. But 30, 390, 750 would all be coterminal angles because they start and end at the same place. That much makes sense? All right, moving now to that formula page that I provided for you. We've got, what was it, 19 formulas, I think, that we'll go through today. These should pretty much all be review of things that you have seen before, beginning with supplementary angles. So you can draw in a picture for that. Supplementary is if you put the two angles side by side so that they share one ray, so that the terminal side of one is the initial side of the other. Then once they are lined up, those other two outside rays form a straight line. The sum of the two measures is 180 degrees. You will have quite a few homework problems that say the supplement of an angle is 5 times something else. So you're going to need an expression for that supplement of the angle equals 5x in there. So if an angle and its supplement add up to 180, the supplement is 180 minus the original angle. So you'd simply say 180 minus a equals 5x in the example I was making up as we went along there. Complementary angles will be the ones that make a 90-degree angle if you put them together. Measure of angle C plus the measure of angle D is 90 degrees. For supplementary and for complementary, they do not have to actually be side by side. We could have one angle here, and we could have the other angle, so I can draw that approximately right about like that. So I could still have them separated like that, and they would still be complementary. Same thing for supplementary. They do not have to be written side by side where they share one of the sides. And yes, Emerson, let people pretty much get this copied down, and then I will go back to that previous slide for the coterminal angles. And you've already got written on your paper that if two angles together make 90 degrees so that they're complements, if you want the measure of the complement, you'd do 90 minus A, just as we did 180 minus A for the supplement. Sometimes students struggle to keep straight which is which, complementary or supplementary. There are a lot of ways you can remember them. What works for me is C comes before S in the alphabet, and 90 is smaller than 180. And that helps me keep straight which one is which, but use whatever works for you. So let me go back to that previous slide with the coterminal angles for a moment so we can finish getting notes copied down. And Emerson, thanks for letting me know that we needed to do that. You're welcome. And does anybody remember from last year what vertical angles are? That was one that we tended to get confused a lot. A lot of times students wanted to call them opposite angles. Vertical angles are when you have two straight lines that cross. It does not work if you have one straight line and then one that bends where they cross. That does not work for vertical angles. They've both got to be straight. And as long as they don't cross at a 90-degree angle, it's going to look like there are two angles that are obtuse and two that are acute. Vertical angles is the reason why the two acute ones have the same measure, and the measures of the two obtuse ones are also equal. So in this case, E and G are across from each other. They're both the obtuse ones in this picture, so they have the same measurement. Same for H and F, having the same measure, those two acute ones. We need to have a reason for our proofs, and the reason will be vertical angles. You did some last year with a bunch of parallel lines, and so we're next going to review what happens with parallel lines. So what we're talking about when we talk about congruent angles with parallel lines is that we have two that are parallel. I can do that little arrow symbol to mark that they're parallel. So two parallel. And then we also have one that goes across both of those, and that one we call the transversal. Whenever we have two parallel lines like that, crossed by a transversal, we get 8 angles. You see I've numbered them 1 to 8. Could have done them in any order. And when I just look at that picture, it looks like I've got 4 obtuse angles and 4 acute angles. And I do, as long as the transversal isn't perpendicular, I always end up with 4 obtuse angles that all have the same measures as each other, and 4 acute angles that all have the same measures as each other. The reason we need all of these names over on the left is so we can come up with the correct reason if we pick 2 of the obtuse angles. Well, why are those obtuse angles the same? Because they are, and then we need a reason. So interior means inside the parallel lines. So 3, 4, 5, and 6 are the ones that are inside the parallel lines. 3 and 5 are both the acute angles, and that's the same measure. And 4 and 6 are the obtuse angles that have the same measures as each other. So 3 and 5 are alternate interiors. 4 and 6 are alternate interiors. They're inside. The alternate means 3 is by one of the parallel lines, and in this case on the right of the transversal, and 5's by the other parallel line and on the left of the transversal. And you may abbreviate in a proof alternate interior angles, AIA. So now exterior angles will be 1, 2, 7, and 8. And it looks like 1 and 7 need to be the same, and 2 and 8 need to be the same. Sorry about that. 1 and 7 are both outside. They're by opposite parallel lines and on opposite sides of the transversal. So 1 and 7 are alternate exterior angles. When we want to say these are congruent, our reason needs to be alternate exterior angles. I recommend not necessarily redrawing that picture each time for these, just writing down the angle numbers on there. Might save you a little bit of time, and since you don't have all that much space on there. Now, I could also, it looks like as I look at that picture, say, well, it looks to me like 1 and 5 have to have the same measure. They're both acute. But they're not both interior, they're not both exterior, so I can't use these two reasons I've already talked about if I want to talk about 1 and 5. Instead, I need to say that 1 and 5 are congruent to each other because they are corresponding angles. And what I do to help me remember corresponding angles is I think of it, well, what if this were a map? And if I had a stoplight right here, angle 1 would be the northwest corner of that intersection where I have that stoplight. And if I came down to, a little farther down the street and there was another stoplight here, 5 would also be a northwest corner of that intersection. So both northwest corners are corresponding, both southeast corners are corresponding, and so on. When you label this in a proof, please do more than CA, because I don't know if CA means complementary angle or what. So put in corresponding angle or something that makes it a little bit clearer which reason you're using. And you see vertical angles. What was that? Yes. Yes, VA is fine for vertical angles. And you do see vertical angles listed again, even though we just talked about vertical angles a moment ago. The reason I listed it again is just as a reminder, when we defined vertical angles, we only had 2 lines that crossed. Now we're talking about parallel lines. Don't forget, you can still use vertical angles. You can cover up and ignore the bottom part of that picture and say, oh, 1 and 3 are the same as each other because they're vertical. 2 and 4 are the same as each other because they're vertical. So by your vertical angle row, simply write in that, get down a little bit farther to get all of them in there. 1 and 3 are vertical, so congruent. 5 and 8, 2 and 4, and 6 and 7. Is it okay for me to go on to the last one in this parallel group? Okay, this last one's a little bit different. We're no longer talking about angles being congruent with this one. I'm now going to talk about pieces of the lines or line segments. And I'm now going to be talking about at least 3 parallel lines instead of just 2. So I've got my 3 parallel lines, and then I've got 2 lines going across them. So A is like this distance from here to here, and B and C and D similarly, just those single little pieces. As long as we're consistent, we can write the proportion a couple of different ways. We can start out with this transversal on the left and do top over bottom, A over B, and then top over bottom again equals C over D when we go over to the other transversal. Or we can go across. We can take both of the top ones, and so let's do left over right, A over C, and then left over right, B over D. Either way, you get the same cross product, AD equals BC, and that's how you can tell that those are indeed equivalent proportions. Now let me show you a weird little way that this is going to show up in some problems, and you might not think that this is proportional line segments when you get to that. Maybe you have a triangle that looks something like that, and you have a line going across here, and they tell you those are parallel. Well, that doesn't look anything like this picture. I need 3 parallel lines, and I've only got 2. And those parallel lines stop. Are those even transversals? Well, yes, they are. We simply want to imagine, well, what if this side of the triangle went farther? What if this parallel line went farther? And then we could draw a third parallel line that just goes through that vertex. So then I could still say A over B equals C over D. So you will have proportional line segments showing up like that in some of your triangle problems. And if you're still working on getting that, just real quickly type wait for me. Otherwise, we'll get ready to go on to triangles next. Okay, nobody's typed wait. Oops, didn't get that one didn't clear. Let me fix that real fast. Okay, thanks for your patience with all my technology glitches here. Who remembers the formula for the area of a triangle? Somebody unmute and just shout it out. Excellent. 1/2 base times height, or base times height over 2. So base can be one of the sides of the triangle. And so can H be this side over here? Type in the chat or shout it out. No, because H has to be perpendicular to the base. But you'd be surprised how many times, even in the advanced class, I get H for one of those other sides of the triangle. Base and height must make a 90-degree angle. They must be perpendicular. Isosceles triangle, you see my picture here. We've got 2 sides that are congruent, but we also have 2 angles that are congruent. And notice that the 2 congruent angles have to be across from the congruent sides. Equilateral triangle has all 3 sides the same, and all 3 angles are the same. And in fact, all 3 angles there must be 60 degrees because they all have to add up to 180. Scaling triangle, no congruent sides, no congruent angles. And as I just said, triangle sum is always 180 degrees. And that just leaves a few circle formulas, and then we will be good to go. So somebody unmute and remind me. Let's see, circumference is when we go all the way around a circle. What's the formula for our circumference? We learned it a couple of different ways. Somebody be brave. What? Well, let's be a little bit careful. Those are both circle formulas. Are they both circumference? So which one would be circumference? Perfect. So the circumference is going to be pi times the diameter, or because a diameter is 2 times the radius, 2 pi r. So depending on whether they tell you the diameter or the radius, you'll either use pi d or 2 pi r. Or maybe they tell you what the circumference is and ask you to find the diameter or the radius. You use whichever one makes sense for the problem. Okay, arc length is going to be part of the circumference, not going all the way around, just going part way around. So we simply want a fraction of the circumference. And we've seen before that in math, whenever we say of, that means times. So we simply need the fraction times the circumference. So here's the circumference, pi d or 2 pi r. If we're only going this part that I've shown in green, that's x degrees out of a total of 360 degrees. So our fraction is x out of 360 times pi d, or x out of 360 times 2 pi r. And then that other formula that we just heard, the area is pi r squared. Helps me keep them straight because this will always have some sort of square units. And this is the formula that has a square in it. I also gave you a picture of what we call a sector. And a sector is like a piece of pie, not just the crust. Arc length is like the crust on the pie, and a sector is like the whole piece of pie. And so again, it would just be the fraction times the area, the fraction times pi r squared. So none of those are too terribly hard, right? Pretty much seen that stuff before. Okay, let's start working some problems, but instead of me doing examples, since there were so many formulas, we're just going to jump into doing a few off of the problem set together. So for the first 50 lessons, you do not have to do numbers 29 and 30 this year. Usually we do those. And if you have a brother or sister who's taken my class before, or a friend, just go tell them, hey, we don't have to do those 2930s in Algebra 3 Advanced this year. And they're going to say, you are so lucky. Those were the most frustrating problems for students. And they're good problems. They make you think. They challenge you. Normally, that's a good thing to have in an advanced class. But with remote learning and all the pressures that we have of that, and it not really giving us as much time, that's one of the things that I've decided to cut this year. It really has nothing to do with the Saxon content that you need to know for next year and the year after. It's just good practice learning how to think things through, good test prep kinds of questions. They are marked out on the sets that you picked up. I'll try to remember to mark them out on other sets that I copy, but I didn't take time to redo all of the PDFs, so where it's posted in Google Classroom, they aren't crossed out. I'll try to remember to write a note. If I forget, send me an email or type something in Google Classroom or Google Chat to clarify that no, you don't have to do that 29 or 30, not till farther on in the course. So let's start together with, we'll do a few of the geometry ones together. Let's start off with number 23. And so you can open up your book and see it. You can also see it here on the screen. We have a radius of a circle, which is pi. So we've got that labeled right here. This radius is pi. The base of the triangle is also pi. And then they tell us the area of the circle equals the area of the triangle. So I need those formulas that we just had. We just had area of the circle, and we're going to write it down as a formula before we start putting numbers in there. Pi r squared equals. And then we're going to write down the area of a triangle as a formula, base times height over 2. Then we can start plugging things in. If this radius is pi, r squared will be pi squared times this other pi out here. The base over here is also pi, so we can change that b to a pi. They say that the height is capital H, and that is still over 2. they want us to find h. So we need to get h by itself. We need to get rid of pi over 2 times h. So easiest way to do that will be to multiply both sides by 2 over pi, the reciprocal of this pi over 2. So the 2 over 2 cancels, the pi over pi cancels. And I think you can finish it up from there and get it in two forms, the pi form and then the decimal form to 3 decimal places. As you finish that, let's take a look at number 25 next. So 25, oh, wait a minute, we didn't go over altitude. What's an altitude? Somebody type it or unmute and shout it out. Great, heard lots of you saying it. I appreciate that. It is just another word for the height. So I can put in here that this is, if I make that a right angle, 3 root 6. And then let's see, I know I've got an area of 18 root 3. So I know my area formula for a triangle is base times height over 2. And I know that that is 18 root 3. And let's see, that means this will be my base. And I need to find the perimeter. Ugh. Somehow I need to get all 3 sides. I've got one side's going to be B, but how am I going to come up with the other sides? Because perimeter is going to be all the way around. Perfect. Because it's equilateral, we know that all 3 sides have to be the same. So these are both also B. So the perimeter is going to be 3 times B. So I simply need to figure out what B is. And if I come over here, this is the one I need. But I know that H is 3 root 6. So I can say B times 3 root 6 over 2 is 18 root 3. So I only have one variable in there, so I need to get B by itself. Kind of like what we saw in the last one, we want to get rid of that 3 root 6 over 2. So multiply both sides by the reciprocal. Let's multiply both sides by 2 over 3 root 6. 2 on the top cancels the 2 on the bottom, 3 root 6 on the top and 3 root 6 on the bottom cancel. So that leaves us with something that's a mess. 18 times 2 is 36 over 3 is how much? 12. And then I've got a root 3 in the numerator and a root 6 in the denominator, but root 3 over root 6 is the same as the square root of a half. So this is 12 over root 2. Can I leave a square root in the denominator? You guys remember how to get rid of that square root in the denominator? Are you good to finish up what B is from there? And then once you have that, plug that in over here and don't forget to label it with centimeters. And you may leave that one in square root form. And we've got enough time that I'll do one more with you. The next one we'll take a look at will be 26. So 26, we have a picture like this. Central angle means an angle where the vertex is here at the center of the circle. We know that that's 40 degrees, so we've got that 40-degree piece of pi. We know that the radius is 3 root 3, and we want the area of the sector. And we learned that that means the fraction times the whole area, so times pi r squared. So 40 degrees out of 360 in the whole circle, pi times r times r means 3 root 3 times 3 root 3. What do I get when I multiply 3 root 3 times 3 root 3? Do we remember how to do that? I know some of the times my brain is still frozen after summer and things I knew real well last year and the year before. How did that work again? Somebody type in, what's 3 root 3 times 3 root 3? Great, I'm seeing some 27s pop up there. To do that, if we take the root 3 times root 3, that is always a regular 3. So that regular 3 times both of these gives us 27. So simplify that. And then also give me the calculator answer. I always want to see it as simplified as possible with pi and the decimals out to 3 places. Make sense?